Assalamu alaikum. Today I will review the Lab 3.6, which is the measuring performance of a machine learning model. So, overview. In this lab is a continuation of the guided labs in Module 3. In this lab you will evaluate the model that you trained previous modules. You will also calculate metrics based on the results of the test data. Introduction to business scenario. You work for a healthcare provider and want to improve the detection of abnormalities in orthopedic patients. You are asked with solving this problem by using machine learning. You have access to a dataset that contains 6 biomechanical features and the target of normal or abnormal. You can use this dataset to train ML models to predict if a patient will have an abnormality. About this dataset. The biomedical dataset was built by Dr. Henry Q. And the first task is in classifying patient as belonging to one of the 3 categories: normal dyschandria or spondylolisthesis. For the second task, the categories dyschandria and spondylolisthesis were merged into a single category that is labeled as abnormal. Thus, the second task consists in classifying patient as belonging to one of the 2 categories, normal or abnormal. So our attribute information is here. Each patient is represented in the dataset by 6 biomechanical attributes that are derived from the shape and orientation of the pelvis and lumbar spine in this order. So we have a pelvic incidence, pelvic tilt, and lumbar lordosis angle, sacral slope, pelvic radius, grade of spondylolisthesis. The following convention is used for the class labels. Dyschandria is DH, spondylolisthesis is SL, normal is NO, abnormal is AB. For more information about the dataset, see the vertebral column dataset webpage. Okay, and dataset attributions and lab setup. Because this solution is split across several labs, in the module you run the following cells so that you can load the data and train the model to be deployed. Note the setup can take up to 5 minutes to complete, importing the data and training the model. By running the following cells, the data will be imported and ready for use. Note the following cells represent the key steps in the previous steps. So we are giving a bucket ID and importing our libraries in here. So from this web page we are downloading and extracting the dataset, and we are writing our dataset into a pandas data frame, and we are using a class mapper to binary label our data, and normals are 0 and abnormal cases are 1. So after that we are moving our target feature into the first column. So the labels, we are moving the labels in the first column for our model to work with. So we are train test splitting in here, and certify is important to have an even split across train test splits and validate split. So we are using a prefix of lab3, and these are the file names we have, and we will use the defined upload S3 CSV function to upload our data frames into the bucket. So we are getting a container instance, and it's a XGBoost algorithm, and now we have parameters in here. So after that we will use the output location in here, and we have constructed our model in here. After that we will use the channels for our files, and we will use XGBoost fit function to train our model, and we are getting our batch, and we are removing the labels, of course. So this is a batch file name, and we are uploading it. The batch outputs are located in here. So the XGBoost transformer will then transform our model. Well, it will predict our batch basically, so we will wait for it, and after that we will save the outputs, and I guess yes. So as you can see in here, we have run it already. So exploring the results. So for the output from the model will be a probability. You must first convert that probability into one of the two classes, either 0 or 1. To do this, you can construct a function to perform the conversion, not the use of the threshold in the function. So we have a threshold in here defined. So and we are getting our data points as in here. Based on these values, you can see that the initial model might not be that good, and it's difficult to tell by comparing a few values. Next, you will generate some metrics to see how well the model performs. So for constructing a confusion matrix, a confusion matrix is one of the key ways of measuring a classification model's performance. It's a table that maps out the correct and incorrect predictions. After you calculate a confusion matrix for your model, you can generate several other statistics. However, you will start by only constructing the confusion matrix. To construct a confusion matrix, you need both the target values from your test and predicted values. Get the targets from the test data frame. So we are getting the test target values. These are the actual values and test labels. Now you can use a scikit-learn library which contains a function to construct a confusion matrix. So we can use a scikit-learn to construct our confusion matrix using the test labels and the predicted binary. So this is our confusion matrix in this format. Your results will vary, but you should have results that are similar to this example. Yes. The previous table shows that the model correctly predicted 8 normal and 7 normal and 18 abnormal values. However, it incorrectly predicted 3 normal and 3 abnormal values. And by using the Seaborn and Matplotlib Python libraries, you can plot these values in any chart to make them easier to read. So let's use the Seaborn and Matplotlib. So we have a color map in here, and we are using a heat map to construct our heat map from the Seaborn, and we are plotting it using Matplotlib. So in here, as you can see, we have predicted classes and true classes, and these are 8 and 19 are true values. Well, the 8 is the true negative, and 19 is the true positive, and we have 3 and 2 as false values. So 3 is the false negative, and the 2 is the false 3 is a false positive, and 2 is the false negative, because Since we have used a mapper to map normal as 0 and abnormal as 1, so abnormal means positive and normal means negative. Tip: if the chart doesn't display the first time, try running cell again. If the results are good enough for your application, then the model might be good enough. However, because there are consequences from incorrectly predicting normal values, that is, no abnormality was found, then there actually was one, the focus should be on reducing this result. Okay, so now I will pause the video. Okay, let's continue from the step 3, which is the calculating performance statistics. If you want to compare this model to the next model that you construct, you need some metrics that you can record. For a binary classification problem, the confusion matrix data can be used to calculate various metrics. To start, extract the values from the confusion matrix cells into variables, and if you extract them as in here, we have 7 true negatives and 3 false positive, 2 false negative, and 19 true positive. You can now calculate some statistics. For example, so for the sensitivity is also known as hit rate, recall, or true positive rate. It measures the proportion of the actual positives that are correctly identified. In this example, the sensitivity is the probability of detecting an abnormality for patients with an abnormality. So, to compute the sensitivity, we divide the true positive by the summation of the true positive and the false negative, and we multiply it with 100 to achieve the percentage. So we have the sensitivity rate in here. So is the sensitivity good enough for this scenario? I might say yes. So specificity, the next statistic is specificity, which is also known as true negative. It measures the proportion of the actual negatives that are correctly identified. In this example, the specificity is the probability of detecting normal for patients who are normal. So it says that the true negative divided by true negative plus false positive, which means there is a 70 chance of detecting normal patients as normal. So is this specificity too low, exactly right, or too high? What value would you want to see here given this scenario? So in this scenario, since the treatments of vertebral column disease abnormalities, the treatments are not that harmful, I might say. Maybe it is enough for 70% might be enough for this scenario. So positive and negative predictive values. The precision or positive predictive value is the proportion of positive results. In this example, the positive predictive value is the probability that the subjects with a positive screening test truly have an abnormality. So we are computing the precision by dividing in true positive by the true positive plus false positive, which means you have an abnormality and the probability that is correct is 68%. So the negative predictive value is the proportion of the negative results. In this example, the negative predictive value is the probability that subjects with a negative screening test truly have an abnormality. So negative predictive value is computed by dividing the true negative to the true negative plus false negative, which means you don't have an abnormality, but there is a 88.8 77 I get, yeah, 77.7 chance that is incorrect. So think about the impact of these values if you are a patient. How worried you should be if the test for an abnormality was positive. On the opposite side, how reassured should you be if you are tested negative? Yes. So the false positive rate FPR is the probability that a false alarm will be raised or that a positive result will be given when the true value is negative. So the FPR is computed like so. We are dividing FP, I mean the false positive with the false positive plus true negative, which means there is a 30% chance that this positive result is incorrect. So for the false negative rate or miss rate is the probability that a true positive will be missed by the test. So the false negative rate means that it is computed by false negative divided by true positive plus false negative, which means there is a 9.5 chance that this negative result is incorrect. So false discovery rate is computed by, in this example, the false discovery rate is probability of predicting an abnormality when the patient doesn't have one. So the false discovery rate is computed by false positive divided by true positive plus false positive, which means you have an abnormality, but there is a 13.6 chance that it is incorrect. So for the overall accuracy, we are computing by true positive plus true negative divided by all cases, which is how well it is performed, and its overall accuracy is 83.8%. In summary, you calculated the following metrics from your model. Okay, we have sensitivity about 90% and specificity at 70%, precision 68, and negative predictive value is 77.7, and false positive rate 30%, and false negative rate 9.5, false discovery rate 13%, and accuracy is the 83.8. So the challenge task is record the previous values, then go back one step and change the values used for the threshold. Values you should try are 0.25 and 0.75. Did those threshold values make a difference? Well, I won't do it now, but it will make difference because the threshold affects predictions of our model. So, well, our model is predicting the same results, but the binary classification function, let me show it in here, 1 second, yeah. The binary conversion changes our results since we are converting the floating point numbers into a binary labeling. So yeah, that's it. And for the step 4, calculating AUC-ROC curve. So the scikit-learn library has functions that can help you compute the area under the receiver operating characteristic curve. So the ROC is a probability curve, and the AUC tells you how well the model can distinguish between classes. The AUC the AUC can be calculated. As you will see in the next lab, it can be used to measure the performance of the model. In this example, the higher the AUC, the better the model is at distinguishing between abnormal and normal patients. Depending on the value you set for the threshold, AUC can change. You can plot the AUC by using probability instead of your converted class. So we are getting the labels from the test split, and we are computing the ROC AUC score. And typically the ROC value is plotted with the TPR against the FPR, where the TPR is on the y-axis and the FPR is on the x-axis. So for scikit-learn has the ROC curve function to help generate those values into a plot. Okay, so we are getting our FPR TPR thresholds from the ROC curve, and we are getting the ROC AUC from the AUC function, and we are simply plotting it using the matplotlib. And yes, let's see the plot in here, as you can see in here. And this is the end of the lab, I guess. Thank you for listening me.